In this video, we're going to discuss two new properties of logarithms. The first one is called the product rule, and what we're looking at is a property that says if I have a logarithm with any base and two factors that are multiplied together in the argument of that logarithm, then I can split that logarithm up into the sum of two logarithms where the argument of the first logarithm is the first factor from that product, and the argument of the second logarithm would be the second factor of that product. And this is a strange looking property, so we're going to begin by proving it. This is a proof by deduction, and what that means is that basically we're going to start with the left-hand side and take smaller, more digestible steps and eventually end up with the right-hand side. And the first thing that we're going to do in this proof is we're going to begin by letting cap A represent a complicated piece that shows up in the middle of the proof somewhere. So we do this is a strategy that has been used in U substitution for solving equations in the quadratic form. We let U be equal to a complicated piece, and then that makes the algebra a little bit easier to look at, and then at the end we back substitute. So similarly, we have a complicated piece that appears in the proof. We're going to let some smaller quantity, let's say B, be equal to that complicated piece. That'll make the proof a little bit easier to look at, and then at the end we'll back substitute to where these things came from. Now, as a consequence of this substitution, I get a different substitution for free, which is that lowercase a raised to the cap A as a power is going to be giving me the argument of this logarithm, right? Because of this that we have let cap A be equal to, we also get that lowercase a raised to the cap A power is equal to m. Additionally, we also get a for free substitution with this second declaration where lowercase a, which is the base, raised to the power cap b is going to be equal to the argument of the logarithm. So we started off with something that just with the intention of making it a little bit simpler, so we're letting cap a and cap b be equal to these logarithms, and then as a result we got these secondary substitutions as well. So let's start the proof by deduction. And by deduction, what that means again is that we begin with the left-hand side of what it is that we're trying to prove, log base a of m times n in the argument. And we're just going to make smaller steps until what we have on the right is what we're trying to achieve. So what we'll notice here is that cap m is what we ended up with when we made that original substitution. We got a substitution for cap m for free, and that cap m is equal to a to the cap a. So let's say that this logarithm then becomes cap m, we're going to use a to the cap a in order to represent that, multiplied by cap n, which is going to be equal to a to the cap b, so we'll multiply that by lowercase a to the cap b, substituting in for that cap n. And now we'll look in the inside of this logarithm. Essentially we have two things that are being multiplied together. They have the same base, and when we have two things multiplied together with the same base, that means that we can add these exponents, right? We add those two exponents in order to write them with that same base a. Now, we're looking at, I'm going to wrap this around to say, let's recopy where we are, log base a of a to the cap a plus b. We're going to now use a property that was established in a different video. So let's just down here recall that the property was log base a of a raised to the r power is going to be equal to r. Remember, a raised to the r power is equal to a raised to the a power in the argument. So we are looking for who is the power that goes on a in order to bring us back to the a raised to the a plus b power in the argument. Well, a raised to the a plus b power is equal to that argument of a raised to the a plus b power. So a plus b, remember, a is what we originally assigned to the complicated quantity log base a of m, and b is what we originally assigned to the complicated quantity log base a of n. And so let's back substitute now for these quantities a and b, and we have a is equal to the log base a of m, and b is equal to the log base a of n. And remember, that is what we were trying to prove. That is the second part of the equation that was the property. So we started with the left-hand side. We kept working on that until we ended up with the equation that was on the right-hand side, and therefore we'll say, essentially, we're done. This little box with an X in it means I'm finished with my proof. You could also use the acronym QED, which is Latin for which was to be proved. I think it's quaerat demonstratum. So this is a similar property. We have the quotient rule. Log base a of m divided by n here is going to be equal to, now, the difference between two logarithms, and this proof is going to be very similar to what we've already established. So we'll start the same way by letting cap A be equal to the complicated quantity that occurs in the proof, log base A of m, and cap B be equal to, again, that another complicated quantity that occurs in the proof, so log base A of n. And as a consequence of these substitutions, we get another substitution for free, which is a to the cap A power is equal to m. And as well, we'll start with the base A, raise that to the b power, and get n, so a to the cap b is equal to n. We go back to the beginning, and we're going to begin with the left-hand side of what is to be proved, and we're going to prove by deduction, taking smaller steps until we land on the right-hand side, right? Land with what it is that we're trying to prove here on the right. So we'll start by saying cap m has a substitution that is a cap a, right? So this is going to be log base a of a raised to the cap a power. And then cap n is going to have a substitution of a to the cap b power. So we're going to replace cap n with a to the cap b. And then we'll say we have that property of exponents that tells us if I have two things that are being divided that have the same base, I can combine that using the same base a where I subtract their exponent. So this is the same thing as a raised to the a minus b inside the argument of the logarithm. And so let's wrap that around here to continue with our proof. So we're going to end up with now the same property that we had a moment ago. A raised to what power is going to be equal to a raised to the a minus b power? Well, that's going to be a minus b, right? A raised to the a minus b power is a raised to the a minus b power. So now we back substitute, going back to what a represented originally. Well, originally we had a being equal to the log base a of m, and originally we had cap b be equaling to the log base a of n, and so we'll replace that. Cap a is the log base a of m, and cap b is the log base a of n. And remember, we started this all off with the left-hand side, which was the log base a of m divided by n, and that's equal to what we have now. So this is proven, and we'll finish it off with this little box here, or again, you might in some textbooks see QED marking the end of a proof. So let's do two quick examples to show how this works. So in part A, we have essentially a division problem in the center of the argument. So we're going to split this using that quotient rule, and the quotient rule says that we're going to be looking at the log with the original base, base 4, of the top piece, which is 16. So it's the log of the top minus the log of the bottom, and we're using the same base that was present in the original problem. So it's log base 4 of 16 minus log base 4 of y. Again, we'll just state up here that we are going to be subtracting top minus bottom here. And then, so we've got the log base 4 of the top minus the log base 4 of the bottom. And when we scan back through to see if there's anything else we can do to expand this logarithmic expression, what we see here is something that we know what the value of it is, log base 4 of 16. The log base 4 of 16 is going to be equal to the exponent that goes on the 4 in order to bring me back to the 16. Remember, 4 raised to what power is equal to 16, and 4 raised to the 2 power is 16. So this has a value of 2. So we're going to replace all this with its numerical equivalent, so 2 minus the log base 4 of y, and that is what our original was equal to. So we'll say that we are finished expanding and simplifying this one. Let's expand and simplify the next one. And in this next one, we basically have a product. So this is going to be our product rule. And the product rule says that we can expand this into the sum of two logarithms. Both of them are going to have the same base as the original. Now, the original base was 10 because there's no written base. That means that it's implied base 10, right? So this is log base 10, but again, we don't have to write base 10 because of the shorthand that we're using. Log base 10 of the first factor. Well, the first factor is 100, so we're looking at log base 10 of the first factor, plus, because this is a product, the log base 10 of the second factor, which the second factor is just going to be x, right? So now we scan back through, we've expanded it, but we're going to scan back through to see if there's anything that can be additionally simplified. And let's just notice over here that the log base 10 of 100 is going to be equal to 2 again, because 10 raised to the 2 power is equal to 100. So this has a value of 2, and we're going to then add the log base 10 of x to that, and this would then be our expanded and simplified version of what we originally started with.